Lesson 114. In this lesson, we're going to learn how to multiply and divide complex numbers in polar form. So let's start by looking at multiplication. I have complex numbers, Z1, Z2, and let's multiply them. So I have R1 cis theta 1 multiplied by R2 cis theta 2. What I'll do is now I write them in rectangular form first. So R1 cos theta 1 plus I sine theta 1 multiplied by R2 cos theta 2 plus I sine theta 2. What this allows me to do is to multiply the two moduli together. And now I'm going to expand the binomials. Okay, so cos theta 1 cos theta 2 plus I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2. Now I square is negative 1, so sine theta 1 sine theta 2. What I'll do next, I don't need the round brackets. What I'll do next is to group the real parts and the imaginary parts together. Okay, so cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, these are real, and then plus I have cos theta 1 sine theta 2 plus sine theta 1 cos theta 2, like that. Okay, and many of you will probably recognize the following. Cos minus sine is cos plus two angles. Okay, so that's compound angle formula. And then what about the imaginary side? Cosine plus sine cos, it would be sine theta 1 plus theta 2. This is significant because, look at this, when I'm multiplying two complex numbers together, I am multiplying their moduli and I am adding the arguments together. Okay, so let's summarize this in a box. And you add the arguments. Okay, I will also put a box to highlight our result right there. Okay, let's put this into practice. So determine the product of 3 cis pi over 4 times 2 cis pi over 2, and then plot the result. So here we multiply 3 by 2 and we'll add the angles or arguments together. This is 6 cis, this is really 2 pi over 4 plus pi over 4, so 3 pi over 4 in the second quadrant. So if I plot this on the argand plane, the real imaginary axis is here. This is 3 pi over 4, and this is 6 cis 3 pi over 4, like that. Okay. In example 2, I am given Z1, Z2. I want to multiply them in Euler form, so let's write both of these into Euler form, meaning that for Z1 it's 1 and 1 plus I. That means I have 1 square plus 1 square all square root as the modulus, root 2. And then what is the argument here? So 1 and 1, so it's pi over 4. In the first quadrant, and obviously Z2, I can easily convert that polar form into Euler's form. Okay, so Z1, Z2 would be root 2 EI pi over 4 multiplied by 4 EI 7 pi over 4, like that. Okay, so here we have got 4 times root 2, right? Multiply the moduli, but we add the arguments. If you also think in terms of exponent laws, right? You're multiplying 2 powers of e. So you add the angles or add the exponents. So we have not defined anything mathematically even when we're working with complex numbers. Okay, so this gives me 4 root 2 e to the I of 8 pi over 4, so 2 pi, which is right on the real axis. So the simplified form is the real number 4 root 2. Okay, next, we're going to look at division of complex numbers. So given Z1 and Z2, if you recall from year 1, as we divide two complex numbers, we multiply by the conjugate of the denominator over itself, okay? Because this will then give me Z1, Z2 star over the square of the magnitude of Z2, okay? So what does this mean? Well, Z1 is R1 cis theta 1. How about Z2 conjugate? From lesson 113, we learned that all we have to do is to keep the modulus and take the negative, okay, of the angle theta 2. And then obviously the square of modulus of Z2 is R2 squared. This means that I can reduce one of the R2s. What does that mean? The multiplication says I will have to add the arguments of the two complex numbers. So giving me R1 cis theta 1 plus negative theta 2 divided by R2. This is very important because as you can see here clearly, dividing two complex numbers in polar form really mean that you will have to divide the moduli and then subtract the arguments. And because this is important, let me put a box around it. Okay. So let's now turn to example 3. Given a complex number in polar form, let's find Z star, the conjugate. So like we said earlier, we know that Z star means that same modulus as Z, but negative of the angle. Okay, there's nothing wrong with using a negative angle because it is common to see theta going from negative pi to positive pi. But let's say we want everything in positive angle. I can easily convert this by doing 2 pi minus 11 pi over 12. So this is 2 pi is what? 24 pi over 12. So 24 minus 11, 13 pi over 12. Also good. All right. Part B, we are looking for 1 divided by negative Z. Okay, so 1, I know that is cis 0, right? It's a real number, so argument 0, modulus is 1. What about negative Z? Well, let's see. So Z is 11 pi over 12, so it's in the second quadrant. And from lesson 113, we learned that negative Z, and it makes sense, right? The real part will become from negative to positive. The imaginary part will go from positive to negative, right? And also the relationship between Z and negative Z is they differ by pi radians, okay? We could rotate clockwise. We could rotate counterclockwise, right? Because it doesn't change the relationship between Z and negative Z on the Argand plane. This time, however, I'm going to go into the negative argument for negative Z because when I'm dividing this complex number, I know I'll be subtracting, right, the angle. So that means that it's actually easier to work with that. So cis would be 11 pi over 12 minus theta, like that. Okay, so what does that mean? That means this angle here is what I want. This is 11 pi over 12 minus pi. All right. And this becomes what? Negative pi over 12? And this works out nicely because let's divide the moduli, 1 over root 2, and let's subtract the argument, 0 minus negative pi over 12, which is just pi over 12. Just like that. Okay. And now last but not least, we are going to find Z1, Z2 conjugate over Z2 with the given complex numbers. So Z1, let's write this in Euler's form first to match what Z2 is written as. So I am at negative 2 and 2. So this is in the second quadrant, isosceles, right? Triangle here. So that means that one can be written as 2 squared plus 2 squared is 4 plus 4, 8. So 2 root 2. And then, not cis, but let's use Euler form. So e to the power I. This would be 3 pi over 4. Okay. I think the operation will get a little long. So why don't we just do Z1, Z2 first, okay? And then slowly piece everything together. So Z1, Z2 means I have 2 root 2 EI3 pi over 4 times 4 EI 7 pi over 6. This is 8 root 2 E. Now, we can think of this in terms of, the rules for multiplying complex numbers, which is to add the arguments. Or even if we go back to look at, well, can we treat this like an exponent law? Like we're multiplying 2 powers of E? Absolutely, you add the exponents, right? So here, 3 pi over 4. So let's turn this into over 12. That would be 9 pi, and 6 would be times 2, so 14 pi over 12. So this gives me 8 root 2 EI. This is 23 pi over 12, like that. Which means that now we know the trick for finding conjugates, which is really just to take the negative argument, okay? So once I have confirmed Z1, Z2 conjugate, then I can use that to find our final answer, right? So here, 8 root 2 e to the I negative 23 pi over 12 divided by 4 e I 7 pi over 6. So 8 divided by 4 is 2, so 2 root 2 e. Here I have I of negative 23 pi over 12 minus over 12, so 14 pi. This is a really big negative number of negative 37 pi over 12. And of course, I don't like dealing with numbers like that, right? Because it's kind of awkward. So let's find a simpler representation of this. If I want to turn this into a positive angle, I think my best bet is actually to use like 4 pi, because that would be 48 pi over 12, like multiples of 2 pi, because you want coterminal angles. So if I do that, what will I get? I will get 11, right? Yeah. And this is the simplified form of Z1, Z2 conjugate over Z2.